the solver will find the nodal temperatures using a procedure similar to what we saw in the big ideas in FEA. So it'll go from the boundary value problem to a system of algebraic equations in the nodal temperatures. And it'll do that using the piecewise polynomial approximation for t that I just talked about. And each algebraic equation will relate a nodal temperature to its neighbors. For instance, if I consider this particular node, when the solver derives the algebraic equation for that node, it'll relate this node to its, the nodal temperature. Let's say if this is 3, it'll relate T3 to the neighboring temperature values. And to see which temperatures will be related, we can use a principle that I discussed in the big ideas. So you look at all the elements that are attached to that particular node. So we have 4 elements attached to that node. And then you pick out all the nodes that are attached to each of those elements. So this element is attached to these 4 nodes. This element is attached to these 4 nodes. And then you have these nodes coming in and these nodes. Which means that the algebraic equation at this node will relate T3 to these other values. This node is not connected to this element, so for instance, those nodes won't be involved in writing that relationship. And we also know that there's going to be a constant term that comes from heat generation. In this case, we don't have heat generation, so there won't be, the algebraic equations won't contain at this node. The algebraic equation at this node won't contain the any constant term. And once the solver generates those algebraic equations, in fact, it will, it thinks of it in the matrix form. The temperature vector, for instance, in this case will be, you have 16 temperature values. So this will be a vector with 16 rows in one column. The stiffness matrix will be a 16 by 16 matrix, and so on. And similarly, you can think about what's the dimension of Q. And it will invert that, so that's a matrix inversion problem, and determine the nodal temperatures. So you'll have the 16 nodal temperatures, and everything else is calculated from those nodal temperatures through post-processing. So for instance, you can find the temperature at any location through the interpolation from the nodal temperatures, and then you differentiate that, you can get the heat flux. And the heart of the method is going from the differential equations to a system of algebraic equations. Let's think about how the process that we discussed in the big ideas in FEA gets extended to this to the 2D case.